Hi, this is Dick Meehan. In this short video, about 10 minutes, I'm going to look at the seismicity of part of the San Francisco Bay Area near Calaveras reservoir, east of Fremont. I mean to illustrate here some desktop techniques of displaying earthquake data and also to introduce a few ideas of my own from engineering mechanics, which is my principal background. Any departures from orthodox geological or seismological ideas may thus be taken as the innocent fancies of a mechanician, not a scientist. Superimposing here a map of microseismicity from a 2010 paper by David Oppenheimer and colleagues at the U.S. Geological Survey and UC Berkeley on the 2007 Alum Rock earthquake, which occurred on the Calaveras or Calaveras-Hayward fault. To the right, the vertical line we see demarks the fault on which the Mount Lewis earthquake of 1986 occurred. Here we can see on this illustration some fine detail. Many of the events that occurred in the ground between these two faults, the Calaveras and the Mount Lewis, are only magnitude 2 or less, but they do reveal an orthogonal pattern. This was observed in 2002 by Princeton geoscientists Deborah Kilb and Alan Rubin in a paper dealing specifically with the 1986 Mount Lewis earthquake, which was, by the way, 5.7, very similar to the Alum Rock earthquake. But I claim here that this pattern is extensive and characteristic of a regional stress pattern as follows. I'm going to introduce an imagined feature called an indenter, a big spike that is being wedged down from somewhere around Mount Diablo. Alternatively, one may look at this as California trying to flow up to the northwest around a stubbornly resistant block. This so-called transpression stress pattern is also compatible with a imagined blind thrust fault under the hills, which as far as I know has not been proposed in this particular geography. I'm adding to this picture a lightened square zone of topography to which I will return shortly. But first, I want to show, in support of this indentation idea, an example, in fact, the flagship example, which was proposed in Asia by the French geologist Taponnier back in the 1970s. In this case, the Indian subcontinent is the indenter, and the inset diagram in the upper corner is a response to this indentation as if the Earth's crust were a plastic material, an engineer's view of things. I'm going to flip this diagram both horizontally and vertically so that the indenter, in this case the Indian subcontinent itself, is up on the right-hand corner, moving down, as I surmise, for the case of Mount Diablo. Note that the fault pattern in the Red River area of China corresponds geographically to the area around the Calaveras reservoir, and also contains rectilinear faults. This concept is worth looking at in other parts of California. For example, here we see Southern California and the Central Coast ranges on the left, and a comparable pattern of response derived from soil mechanics showing a indenter or deep foundation pile being forced down into a plastic substance. Now, with these hills being squeezed from the northeast, we appear to have three potential earthquake sources. The first is the obvious Calaveras-Hayward fault trend, with either characteristic magnitude 5 to 6 repeater earthquakes, like the Alum Rock, or perhaps a much larger earthquake involving a longer slip, giving rise to stronger, long-duration ground motions that are damaging to many strain-weakening types on account of their long period or duration. The second type of earthquake, which I'm not going to go into here, is a potential blind thrust under these hills. And finally, we have this pattern that I previously introduced of a conjugate set of near vertical faults at roughly right angles, the orthogonal faults I discussed earlier. Now, returning to that lighter colored square area that I brought up previously, I'd like to look at that next, this time including more recent epicenters through the year 2011, shown in the vicinity of the dam site. Now, this image suggests that these epicenters are near the ground surface, which is certainly not the case, so it would be nice if we could fly around underground, which I will now proceed to do. Now, the ones you are seeing here are from 5 to 10 kilometers deep during the period 1984 to 2011. And you can see that they, at least on the west side, define a clean Calaveras-Hayward fault trend. But viewing the pattern in detail, it appears that the residual earthquakes, most of them quite small, are far from random or uniform in their distribution. Viewed in vertical section from the south, the hypocenters at the location of the 2007 Alum Rock earthquake form a pattern like a necklace of beads. And in this view from the south, we see that the beads themselves are also non-random clusters, also with a necklace-like pattern, suggesting overall a fractal organization in space. These little things seem to float around like free birds, but in fact they are not free at all. They are all part of the plan, as someone, was it Walt Whitman, liked to say. In fact, if you measure the relative dimensions of the open spaces, which I take to be stuck patches corresponding to a hierarchy of earthquake magnitudes, you arrive at a cumulative distribution of dimensions with a B value, very similar to the Gutenberg-Richter law. I don't distinguish between magnitude here, but it would be nice to supplement this view by adding a measure of magnitude dimensioned at least roughly in accord with the size of the slip involved for that particular magnitude. That is to say, about 3 kilometers diameter for a magnitude 5. Even better that we show this pattern as it emerges over time, which I've done here in 2 different ways, as a cross-sectional view looking to the north on the left, and as a timeline moving to the right on the right side. The left pattern, a north-looking cross-section, has the shape of South America and the 2 magnitude 5+ earthquakes, the first occurring in the 1980s, located in the equivalent of Brazil, and the second, the Alum Rock earthquake in Peru, are thought to be 30-year repeaters. But at the top of the seismogenic zone, at the level shown by the yellow double-headed arrow, a smaller bird chirps away at a faster pace of 1 every year or 2. Similar geological structures appear to generate similar patterns of aftershocks, as in the case of these two, which I have isolated for inspection. The western event, a 4.1 magnitude, occurred beneath the reservoir in 2010 and matches, in many respects, the smaller so-called sliced bread fault discussed by Kilb and Rubin in their paper on the 1986 Mount Lewis earthquake. So it is, we get a glimpse here of the music of the spheres.